Okay, how's everyone doing today? Are we having fun yet? Huh? In the project? You're all like 80% done now, right? I can make it due this Friday? We're good? Good. Questions on it? Christine?
Things that's because like all of you can have like maybe studies and I'm not going to be doing you but not maybe like studies.
So the namespace is like the type of page it is, or the type of object it is. So if you look at, the Wikipedia namespaces, there's a list on So if you look at the Wikipedia namespaces, there's a code and there's a type of article or a type of page that's associated with all these codes. So a namespace is just a number that encodes which type of data it's talking about. So most of these are going to be the zero namespace, which is an article, and the one namespace is a talking, whatever. So that's the only thing it refers to.
And the join that is that was getting the previous link notes.
So the join that we did last class was between the link target table and the page table. So if you look at the link target table, it has a link target ID and the link target title and the link target namespace. The link target ID is just the ID of the row in the link target table. It doesn't have any meaning outside of that. In the page links table, it has the source node in that edge in the Wikipedia graph and the namespace of the source node in that edge. Like the namespace isn't strictly necessary to do this matching, but for some reason, it's there. Maybe they have some optimization that relies on the namespace or something in Wikipedia, but you don't really need the namespace in this project. The page link target ID is the destination of a link in a page. And the page link target ID refers to a link target ID in this table. And so I don't know why they chose to implement it this way. I'm not sure why they have, because the page links table is only links between pages. So they could have just put the page ID here, but they didn't. I can't tell you why. That's what the name is. And so you're going to have to join the link target table and the page table to get the page IDs of the link targets because they have the title and the namespace of the link targets instead of the page ID, in spite of the fact that the page ID would be smaller and more efficient to transport around. So I'm not sure why they did it that way either. Page link from is the page ID of the page that's doing the linking. So if you have a Yeah, so if you have a link from polar bear to the Arctic article, then the page link from would be the page ID of the polar bear page, and then the page link target ID would be the ID of the link target that belongs to the Arctic article. But that's not the same thing as the ID for the Arctic page.
That other table that where you reps because if you just did the rep table but like that way you can go from the new target because it isn't it the reps are we directing the links.
Not really. Well, the redirect table is something else because the redirect table, it has, um, I believe it has the ID of the table it's being. We can actually just check what the schema of the redirect table is. The link target table is not responsible for redirects at all.
Yeah, I do that. Okay, let's have that.
Okay, so, oh, I didn't. So the redirect table specifies like this page redirects to this other page. So, think this page, demographics of Afghanistan links redirects to population of Afghanistan, something like that. They have a lot of redirects that look like that, where it's just rewordings. Yeah, that's the redirect table.
So the redirect from writes the page ID.
Yeah, redirect from is the page ID of the page that is redirecting to another page. The redirect title is the title of the page that is being redirected to. No, it gives you the title, which is stupid because it means you can never change the title of a page without updating a billion rows. It's so dumb. That's the fascinating thing about real world data sets. They're all just horrible. Our data account is horrible. We put a lot of work into making it not horrible. People giving us just random crap all the time. We have an email with like 50 dots in a row in it because somebody's committing fraud and adding a new dot every time they make a new email. It's so funny. Any more questions?
Did you did you just figure out what these were like from the data or is there like a schema somewhere that you
So there is a schema. There's documentation on all of these tables if you need it. So you could do it's not super easy to find. It's like we have a database download and then oh no, that's the actual data. But then there's a page somewhere on the actual schema of everything. Let's just look at Wikipedia. That is not helpful. Database layout? Maybe that's what we want. Close. Oh, here we go. Okay. Yes. All right. So this is the documentation entry on the page table. And it'll tell you about all of these columns. And you'll notice that the prefixes in S3 are the exact same as the names of the table from Wikipedia. Yeah. So we can look at link target table. Okay. Okay, the page table. This table stores a page namespace title tuples, each one with a unique integer ID. This table is used for referencing page titles in tables and tracks the links to pages. Not sure why they structured it this way. And the page links table was actually not present in the dump that I downloaded. These two columns are not present in the dump that I downloaded. So this is just a foreign key to link target, and this is the namespace and the page ID of the page containing one. So all this information is here, and all of it's documented. And your job is to parse through it. So that's part of the problem when you have a data set like this is you have to spend quite a bit of time understanding how it's structured. And so the only thing I did for you was to take it from the SQL dumps and put it in S3, which was an absolute chore in and of itself. I remember telling you that it took like 3 days for one of these things to import. It took like 3 days for the page links table to import into my SQL. It was so lame. I don't know why. So you can find all the documentation over there. Anything else? Hmm? Yeah, you can't keep it running. If you keep it running, we're gonna run out of money real fast. So every time you're done using it, you have to stop it and then restart it again when you're ready to start using it again. And the way you can restart it is really easy. You can just clone the cluster. So after you terminate it, you can clone the cluster again, and you won't have to put in any of the configuration information. All of it will already be there for you. And it'll be the exact same thing. It'll have the same instance types, the same number of instances, and everything. So you just clone the cluster and it'll recreate a new cluster. That's actually how I created a cluster for this class right now. So you can use that option if you don't feel like filling in all the details over and over and over again, because that's annoying. So you can clone the previous cluster. So yeah, don't keep your cluster running for longer than you actually need it to be running, because if you charge too much money to our AWS account, we're going to have an unpleasant conversation. And I don't want to do that. So let's not go there. Anything else? Okay. All right. So we left off with exploring joins to this link target table. And we left off with, this persisting to memory and disk and all that. And it was fun. So this is something that I've also showed to the data scientists at work is I have a lot of helper functions that I like to use to speed up my development process because I'm too lazy to type everything out all the time. So one other method that I have, and what's really cool in Python is you can actually add methods to existing classes, which is cool. So you can add methods to the PySpark data frame class. So that's what we're going to do. So we're going to add a method called save, and we're going to have the name of the table that we're saving, like as a SQL table. What just happened? I never told you to do that. Yeah. We're going to have the name of the table we're saving. And what this is going to look like is we're actually just going to take this part and make that part of the save. So what we're going to do is we're going to import a bunch of stuff from we're going to import a bunch of stuff from S3 or anywhere else. And since this is a method, we're going to have to add the self keyword. So we're going to say self.persist.creator replace temp view and whatnot. And so we can create that view, which is assigned to, this is called name now. And so this will enable us in like a chained operation to just save any data frame to memory in an eager fashion. So we'll pre-compute everything because we're calling an account function. And so then all we need to do up in the Parquet thing is to call files.save and with whatever prefix we have. That shouldn't be a string. Now, the way we do this actually differs between when we want to run this kind of thing interactively, or if you want to use these helper methods in non-interactive EMR. So if you want to start EMR and then submit a job to EMR, this process looks a little bit different because when we submit jobs to EMR, we're not using Spark Connect. So they're actually two different classes under the hood. The class that of the data frame that communicates with Spark Connect is technically different from the class that communicates without Spark Connect, even though they both have the same interfaces to both data frames. So right now, what that looks like is I think it's PySpark.SQL. Actually, you know what we can do? We can just say PySpark table of, we don't have one target. We just read a redirect, right? That's looking nice. Bam. Okay. So what we can do is eventually we'll just be able to say with any data frame, you can call it any data frame dot save to this SQL table. We're going to say PySpark.SQL.connect.dataframe.dataframe.save equals save. So we're literally just giving it a new attribute, and this object knows that that attribute is a method. So we can do that. PySpark is not defined. Lovely. Okay, now let's see if this works. So if we go down to our link target and we want to do an inner join to actually get the page IDs of the link target, what we're actually going to do is we're going to save this as link target page. And something broke. Let's see what broke. Link target table. Oh, we didn't load the link target table link. That's why. We have to load these two guys in here. Load the link target table and the page table. And that'll take a minute. Everybody good on the joins from last time, the different types of joins and what they do? Good.
Say this as a mistake and send it to me. It runs this, it define that with the other class, and they can write two different versions and stuff.
No, you don't have to write two different versions of the save function. You just save it to a different class. So on Spark Connect, it'll look like this. And on EMR, when you're running it as a step, it'll look something like this. That's the only difference.
So in order for to if we need to do something which is by the first program to run, then you know to run for you, then you need to define these values.
Well, not necessarily both ways. So when you're running it interactively, like when you're just experimenting, use this version. But if you want to use these helper functions in your submission, which you can, do it this way so that, it'll actually acknowledge it as a method that you've added to the class. Okay, it looks like we got everything. So now, there we go. So we created this new save function or this new save method on the data frame, which didn't exist before. And we can do whatever we want with these custom methods. Now, I think this is pretty cool, and it's a pretty cool way to extend the syntax of Spark to basically do whatever you want. Another cool thing about Spark, which we may or may not get into, is the fact that you can take its schema and parse the schema as an object. And so I've done all sorts of like code generation and reflection with that kind of thing to automate the stuff even more. So something I did a while back was, do you all know what DynamoDB is in AWS? It's basically like a hash table on a distributed system. So it's basically a giant hash table. And it's a database that has a particular like type of schema associated with it. You need the JSON to be in a very specific format in order for the database to actually accept it. So what I did was I wrote a piece of code that can take any schema from Spark and automatically translate it to a schema that works for DynamoDB. And it works in the exact, it's just a method call now. So it translates between the schemas, and now it's literally just a method call that you can call in Spark, just like everything else that will translate between these schemas. So adding methods can be super powerful, and it can save you a lot of time. Because now, whenever I need to import something into DynamoDB from EMR, I just use that function, and it works for everything. So I only had to write that piece of code once. Because if I had to write it every time, I would probably want to quit my job.
So for all of these functions that you're writing, I just didn't want to have to go grab things that I didn't need to do environment. So probably becoming on the all future notebooks that you want to do.
I just copy and paste them into notebooks.
Seriously?
Yeah. I mean, that's the easy way to do it because the alternative is because I usually don't go back to my old notebooks very often. Most of the time, I either abandon that project or I promote it into something that's actually usable in production. And the production stuff doesn't usually use these helper functions very often. Because it's mostly just for programmer convenience for the it's um I thought about it. I thought about like creating my own library and then like pushing up the library and then like importing it in every notebook and stuff like that. But that's such a pain because every time I want to make a minor change to this because I figure I want to add commas in this number that I'm printing out, then I have to, change the code in the library, commit it, and then pull it down again and import it again. So I didn't feel like doing it. So I just copy and paste it. Okay. Questions on adding new methods? And this works for a bunch of different things in Python, not just the data from class. I think the only thing that you can't do this with is the built-in types. I don't think you can do this with the built-in types. And I'm pretty sure you can do it with basically everything else. So you can't add a new method to like Python's list class. Questions? I think it's pretty cool. I love how you can just do all this random hacky crap in Python you can never get away with in any other language because Python just lets you do whatever you want. Not necessarily for a good reason, but it does. I remember like yesterday, I had to do some really stupid stuff in Python where I was trying to do you guys know what protocol buffers is? Protobuf. So it's this binary serialization format that we use for our web services for gRPC. So it's a binary serialization format. It's compatible with JSON, but the binary format is really compact. It's very small, like for the amount of stuff that you're trying to store. And what I wanted to do was we were trying to create all of these database objects and I wanted to serialize them in protobuf. The problem is the serializer in protobuf is not serializable. And so when I was trying to write a UDF in Python to serialize stuff like to the protobuf format, Spark was telling me, hey, I can't actually send this function to other machines because the function itself is not serializable. Because the protobuf serializer isn't serializable. So what I had to do was I had to make sure that the protobuf serializer was already available on the executor nodes before I sent the code over. And then what I had to do was something like this. Like I had the UDF, and then in the UDF, I had to do the import. It was so dumb, but it worked. So, huh? The bootstrap script.
In the bootstrap script, you can tell where the stuff is data. You can specify it in the script.
It was just a pip install. But yes, you can. The bootstrap script is like literally just a bash script. You can do whatever you want.
Control because Spark is the one. Okay, let's see. Bootstrap. Go my bootstrap scripts line have four and have Spark server has started.
Yes.
So is it the Spark server the one in charge for the executors?
No. So the executor is an abstract idea that's kind of disconnected from the nodes in EMR. So the nodes and the executors are not the same thing. The executors are the Java processes that Spark manages to do the computations. The nodes are the machines that the executors run on. EMR manages the nodes, Spark manages the executors.
Okay, so you're saying that you were able to, within scripts, install at the executor level, there's the four Spark is running, even though Spark is the one who manages the executors.
Yes.
So
it's installed on the node. So even if the executors die and then restart, it's still available on the nodes because the executors run on the nodes.
Installed it on each node.
Yes. So the bootstrap script is a feature that's available in EMR if you need to do something more advanced. So we don't have any bootstrap actions in this class because we don't really need to do anything that complicated or that custom. But what we have at Count is we have all of these custom libraries that we've written in Python, and we need to be able to use those in our Spark programs. And so we have a bootstrap script, and the script is literally just a .sh file that lives in S3 with a bunch of pip installs in it, among other things. And this script runs on every node in EMR before the cluster starts up. And so it adds all of these packages that we need in order to, run the code.
All of the scripts are running on each node.
Yes.
So would your cluster span time be larger if you have no nodes?
Not really, because it's all done in parallel. Like all the bootstrap scripts on every node, they're run at the same time. So not really. There is one exception that happened, and that is where we had a bunch of files running in network elastic file system. Like, is there no search bar? There's the search bar. Managed file storage for EC2. Okay, so elastic file system is a network file system. So it allows you to create a file structure in a distributed system, which is really cool, except for the fact that it has limited throughput. So what we are trying to do is we have all of these files that are full of data from a company called Melissa Data. Melissa Data has information on deliverable like US addresses, like US street addresses for houses and such in its database. And we need to do that for, fraud analytics and things like that. And these files are like 30 gigs a piece. And on every node in the EMR cluster, we need to download all of the files on every node at the same time. So what we used to do is we used to have an elastic file, an EFS file system, which had these Melissa data files in it. So like these 30 gigabyte Melissa data files. And the hope was that we could just automatically create this file system and mount it to all the nodes at the same time. And then we would just be able to use these files. The problem is that before the cluster starts up, these files are not stored on the same machine that's running EMR. So they need to be transferred. And EFS has like limited throughput. So you can only transfer so much data in a specific period of time. And so what was happening is because we had like 80 different nodes running at the same time, it tried to transfer these same files to every node all at once, and the throughput totally tanked because it couldn't handle it. But if we were to take all of these smaller nodes and combine them to a smaller number of larger nodes, you don't have to transfer as many copies. So that fixed the problem. And then we just wound up ditching EFS for EMR entirely because it just wasn't a good solution. And we wound up just downloading them from S3 instead. But that was the stopgap, is to create a cluster with fewer larger nodes so we didn't have to transfer as many copies. So that's what wound up happening. Okay. Questions so far? I know that was a lot of information about things that we've never talked about before, but it's a good story. And I'll talk about EFS all day long if you want me to, but we don't have to do that. Okay. Also, last time we were trying to. Why did it just copy? Okay. You're killing me here. Last time we also wanted to think about whether or not null acted as a join key. And we never actually really got an answer to that question. And it occurred to me walking home after class last time, that there is a way we can look at this in class. So initially we have a link target table, and we had these members of the link target table where the link target title and the link target namespace are both null. So we had, this, let's just copy it. Okay. And we wound up having, these four rows that are literally just all nulls. I don't even know why these are in here, but we can actually just join link target on itself and then see how many rows we come up with to see if it's actually going to join on these nulls. So let's see what happens. We should actually just rename all of the columns in here so as to not be confusing. Target ID as because I'm creative. Target title. Almost never joined a table on itself. This is a weird experience. Okay. And then we can also experiment with inner join and outer join. See what we got. What just happened? Oh, link target namespaces. Did I not actually rename the thing? I did not. Oh, thank, thank you. Okay, so it's not actually joining on the nulls. So it looks like the vision I had last time may have been skewed. So this tells us what actually happened in that incident I was talking about last week, or not last week, on Tuesday, is instead of having like SQL null is different from the string null. So we have, the Python object none and the Python string none. These are not the same thing. And so the problem is, we had one of the data scientists was instead of actually using SQL null, he was using the string null. And because he was using the string null, Spark thinks that that's a valid key because it's a string. And it was sending all of this data with, hang on, I need to snooze. Never mind. Okay. So it's always so disappointing when that happens. So what it was doing was we had like 75% of the rows in this table have a null value for the key, but since the null was the string null instead of actual SQL null, what happened was it was aggregating all of this stuff with this null key onto the same machine, and it was overwhelming it. And this single process couldn't take all of that traffic, so the entire thing was done. The entire thing would run for 2 hours, and then it would run for 2 hours, and then it would have this like 5,000 tasks has finished. You have a single task running, and it would stay like that for like 6 hours and then die. Always fun. So eventually what we did was I think I told you this last time, is we filtered out the nulls before we did the aggregation. We did the aggregation, and then we handled the nulls separately, and then we appended the two tables together afterward. Did I show you how to append two tables in Spark? Okay, yeah, I should do that. So you can append two tables with the union method. So you can use spark.table. We'll just do page. And then we can just append it with a copy of itself. So we're basically just duplicating the table. Union spark.table page. Now, I don't think this is going because some implementations of union in some systems will actually eliminate duplicates, like rows that are duplicates of each other. I don't think Spark will do that. Let's check. So if the documentation says something, and a lot of the time the documentation actually won't say anything because Spark's documentation is not great, I won't lie. You can actually just check. So we can check how many things are in here. That's great. Okay, so let's check the union of these two things. Now, what I'm pretty sure this does is actually just take the page table and appends another copy of the exact same table to it. So it basically concatenates these two data frames together without doing anything else, which is what makes it great if you are not trying to do like an aggregation or something, or like a shuffle, because I don't think this does a shuffle. So we'll check. Okay, so it does make a copy, and it does not eliminate duplicates, because if we union them together and then we did a distinct, then we should wind up with the same number of rows or lower than what we originally had. That might take a moment. Okay, so it's good to know that on a join, at least, it won't do that. But we should also check whether it'll do that on an aggregation. Because if you use the null value as an aggregation key, that could be bad. And that might be what we saw last time when I was working. So let's look at link target. Yeah.
Does it track the distinct values in each of your instances, and then you send that list and compare that list, and then you shuffle it?
Send the list and compare the list.
So you have everything else put out,
Mm-hmm.
and you want to get the distinct value. So it's gonna have to compare them between two all your machines, right? But it could do the distinct on each machine first.
Mm-hmm.
And only send the distinct value from each machine to compare with each other. We'll have to do a shot.
So depending on depending on what you're describing, that may or may not be efficient. So maybe what this does is it might do the distinct first and then send it out. I don't actually know the answer to that question, but it does do a shuffle. And this shuffle works in a very similar way to how the group by statement works, which is where in order to do the aggregation, the group by functionality will take all of the rows with the same value for the aggregation key and send them to the same machine. So if we're aggregating on the link target ID, and maybe that's a bad example, we're aggregating on the link target title. So let's say, we have a bunch of different pages that are called Arctic. One is the article, one is the talk page with different namespaces and so on. And let's say we wanted to, aggregate on that key being the link target title. So Spark will take, and the aggregation key is the link target title. So Spark will take all of the rows with the link target title of Arctic and send them to the same machine. And within that same machine, it'll do the aggregation, whichever aggregation you want. The average size of the page, or it can concatenate all the values together or whatever, but they all need to be on the same machine to do that.
For the next time, like, the ones with the aggregation polar bear to get.
Yes. Well, not necessarily to a different machine, but they're not guaranteed to be on the same machine. That's why.
Ideas of it spreading out in front of you.
Yeah,
That's perfect.
yeah. So a lot of the time we'll do this via hashes. So it'll like we talked about hash values earlier in this class. Is this string Arctic has a hash value. That's too many parentheses. Yeah, the string Arctic has a hash value. And so what Spark will do is it will basically say, it'll be like, okay, I'm going to take this hash value and then I'm going to like take the last 3 digits of this hash value. And based on those 3 digits, I'm going to send it to one of these machines or something like that. And so it'll send all the values with like the same last 3 digits to the same machine because that's what the hash value worked out to be. And that's why data skew on aggregations is such a huge problem, because if you have one key that has a lot of rows associated with it, you get all that data sent to the same sheet. And dealing with data skew has at times been a deal breaker for certain algorithms that we've tried to implement in Spark at count because the data skew is too much. So it's not just the sheer amount of data you're dealing with, is what's the value of that data and how has it been distributed? That's equally important. We have had to cut down the size of certain join keys in order to make them actually possible to join on, right? Because when you join two different tables and you join two different tables on like a non-exclusive join key. So let's say multiple rows might have that value for the join key. That's a quadratic increase as you increase the number of rows that have that join key, right? Because it'll match every row with every other row that has the same join key. So like, let's say in one table, and, let's just say we have the join key and the value is Arctic. And I mentioned the Arctic because I just happen to like cold weather. That's all. And so we have a bunch of values that we want to join together, maybe. So maybe we want to multiply the values in one table by the values in the other table, or something like that. So we have 2, 3, 5, 1, 6, and 7. And in the other table, we have 2, 7, 3, 90, and 10. And so what will happen? Well, the resulting join will have 2 from this table paired with everything else in this table, 3 paired with everything else in this table, 5 paired with everything else in this table, and so on. So the actual number of rows for this join key Arctic will be 30. 6 times 5. And so, let's say we doubled the size of, let's say we doubled the number of rows that each table is contributing to this join key. That quadruples the number of rows that are produced in the join, and so on and so on and so on. So it's a quadratic growth with the amount of data we deal with as the cardinality of the join increases. And that sometimes becomes completely untenable because we've tried to do things with graphs. What if in Wikipedia, I tried to tell you, so in addition to, let's say polar bear, actually, no. Arctic links to polar bear. This is not valid Python syntax. And polar bear links to carnivore. I actually don't know how to spell carnivore. Is this how you spell it? Yes. Okay. Thank you. Okay. So polar bear links to carnivore. What if I asked you to find the second degree connections? So what if I asked you to produce pairs such that you kind of skip a layer? So instead of going Arctic polar bear carnivore, you just go Arctic to carnivore. And you try to find every second degree pair. That's going to be a huge join. I'm willing to bet that is not computationally tenable at all. We can check. We can check how many rows that would produce. Does anyone know how? So let's say we were going to try and produce, this table, this second degree connection table. What kind of join would we do? Well, this table doesn't exist, right? Um, you will have this table after you finish project one. So after you're finished project one, I might share my solution with everybody and we can talk through it if you want. Um, but before that, we're gonna pretend that we have to pretend we do something else. Can I just I wish I had just saved my solution somewhere and grabbed the results so we could do this live. Um, so how we would do this is let's assume that we have, let's see, that we have the page links table because that's the only theoretically that's the only table we would need is page links. I hesitate to do this in class because in order to actually do this live, I would have to do project one right in front of you. So we can see the real result after project one is due. This is why Wikipedia is annoying. But this is also a really good example because in order to do something this simple, you have to do project one first. So we want to join. So what we're going to do is we're going to pretend the page links table has a link between the source page and the destination page. We're going to pretend that these are the two columns. The source page is the page that contains the link, and the destination page is the link that's being linked to. So we're pretending this table exists. It will exist after project one. We're pretending it exists right now. So in order to produce this table, what we would have to do is we have to do spark.table page links, and it would be this, and the join key, or we'd have to join on actually different columns. Nope. You have to do you have to rename this so we don't get confused. Okay. And so we would say the destination page of the first instance of the page links table is equal to the source page of the second page links table. Does that logic make sense? So in this scenario, we'd have two different rows, right? We have Arctic to polar bear and we have polar bear to carnivore. And so in order to make this happen, we would need the destination page of this matched up with the source page of this. Make sense? So that's where this logic comes from. Okay, so at the end of this, we're going to have the second degree links. So this doesn't exist right now, so I can't show you this die. I can't show you this dying, but it will die if we run this on a page links table where we have just the source ID and the destination ID. We could run a little something to find out um how many rows this would produce. I'm pretty sure we can do that. So
Just based on the number of rows in it, like there's a certain limit, because the bench for a certain.
because it's n squared, there's a
Every three rows to every.
yes, yes, yes.
Right, so there would be there are some functional, like if you have two rows in there, I think it's flat. But there's some and above which you can zero.
There are some articles that have hundreds or maybe thousands of links. And so an article that has 1,000 links is going to have a lot of second degree links because it includes all the other pages that those pages link to. So the size of the size of the set of pages as we increase the degree will increase exponentially. Now I want to think, can we actually count it? Can. I think we need the page links table. So here's how I would count it if we had these two. And then we can figure out if we can count it without having the source ID. So here's how we would just count it and not actually generate the table of all these pairs. So how we would count it is we would do spark table of page links. We would have to, oh man. We'd have to look at how many pages have this as a source and how many pages have this as a destination. So we would have to do dot by source page. And then we would do something like join table destination page. Or no, and then the join key would be something like, well, then we'd have to count actually. Source degree. And then we have to do the exact same thing for this one here. So we join these two tables. So what we're doing over here is we're counting how many pages this page links to. And over here, we're counting how many pages link to this page. And then we basically have to multiply those two answers together. Source page equals destination page. Be an inner join. And then we would have to do a with, or we could just do an aggregation actually. Sum of source degree times destination degree and then we can just do a show. So unfortunately, this page doesn't exist yet. But the logic for this is we count how many nodes in this graph that this page points to. We also need to count how many pages or how many times that other pages link to this page. That's going to produce the number of pages that are a second degree link between every page. Make sense? Because up here, we're joining on the source page equal to the destination page of the page links table. So we're basically taking the count of it being the source page and taking the count of it being the destination page. And we need to multiply those things together to get the total number of rows produced for every page that acts as the intermediate link. That's what we're counting. And that's how we would count the number of rows. Sorry for showing this to you too early. We will get back to this. Sometimes no. Sometimes no matter how good your hardware setup is, this is not going to work. Because hardware will scale, your costs and your hardware will scale like linearly. So in order to produce 4 times the amount of data, you can buy 4 times the amount of hardware. But this increases quadratically. And it's why we can't generate all possible pairs of nodes in our giant identity graph that we're trying to build clusters in. Because if we're trying to pair every node with every other node in this huge graph that has 6 billion rows or has 6 billion items in it, what's 6 billion squared? Oh, wow, that is a big number. I don't even know if that fits in a number. And when I say fits in a number, I mean an 8-byte integer. But this is untenable. This is something that we've had to do before. Is we have had to take, because we've had to try and calculate what second degree connections are. We've tried to calculate second degree connections in our graphs before. We have nodes that act as an intermediary between too many other nodes for this to be doable. Right? So like what we're doing to generate these pairs is, we have a central node and we have a bunch of other nodes that link to this central node. And, let's say the edges look like this. So for this node, we're going to see 3 second degree pairings come from this node. The second degree pair is going to be for here, and for here, and for here. And the same second degree pairing will exist for these nodes too. Right? The problem here is that we're joining on this node. Because this node acts as an intermediary, it's the one that can generate this pair. And so we're sending all of this information. We're sending all of the nodes with this as a destination and all of the other nodes with this as a source to the same machine. Now, this is fine because we only have 3 nodes on both sides of this equation, 3 nodes that are coming in and 3 nodes that are going out. But what if we had 15,000 nodes on each side? Because that is a thing that happens in our data. We do have pieces of data that connects to 15,000 other pieces of data. And we can't find second degree connections with this one as an intermediary. So with these really big nodes, we take them out of our data. And then it works. But we have to take these big nodes out of our data when we generate the second degree pairs. That's a perfect example of how data skew has negatively affected our result quality. But we have no other choice because this is too much.
So you go through and figure out something that's vice drafting.
We can't. We have no idea. We just lose the connections. We have no idea that these things, that these second degree pairings actually exist. We take them out because we have no other choice.
So you got people all the things you go with the rest of the note,
Mhm.
the note is the graph.
Yeah, the nodes are still in the graph, but we're acting like these second degree connections never existed because computing them would have taken too long.
So what can you do with like the huge note of it?
Nothing. They stay out for the rest of the process. We can't do anything with them. They're too big. Which might actually be a good thing because a lot of the time these nodes, they turn out to be junk data. Sometimes these nodes are junk data. Sometimes the people who are sending us data, they send us like a dummy value that is fair null, but it's not actually null. So our system doesn't treat it as null, but for all intents and purposes, it might as well be null. Like a really good example is some merchants will send us, how do you spell this? Is it two N's? cnombre@gmail.com. That's just Spanish for no name. And we have like 70 million of these things in our data. And because every transaction we get sent in from this particular merchant contains this email address, that means everything that gets sent in from this merchant is connected to everything else from the same merchant. So we get this giant node with like 40 million different things attached to it just because they have something like this in their data. So we cut these kinds of things out too. So sometimes cutting out these huge nodes is a good thing. Because these pieces of information are not actually related to each other. They just happen to connect in the graph because of this value. It shouldn't even be there. So sometimes removing those big nodes is a good thing. Sometimes. I don't really have much else today. So we can stop 10 minutes early unless we have questions on the project. We can stay for those. Yeah. And we'll do this count after project one. For real. You can append as many tables as you want. You can chain union as many times as you want together. Yes. Yes, they do.
What if I want to
Well, concatenating this way is a join.
or you might not turn to
So pandas is special because pandas rows like they have an index to them. Rows have a number. So rows are ordered in pandas. Rows are not ordered in Spark. So you can do a concatenate in pandas and it'll kind of just automatically join them together for you. In Spark, you have to have a join key. Oh no, I didn't share it. I didn't share the screen.